Welcome. Here I'm going to look at u-substitution for indefinite integrals. So this is going to be a fairly lengthy video. I'm going to talk about what u-substitution is, and then I'm going to do at least 5, maybe 6 example problems, starting with some basic u-substitution and going to more advanced types of problems. So the first things first is that u-substitution is a method of integration that is the reverse process of chain rule. So it kind of undoes the chain rule. So remember that when you have the chain rule, let's just go ahead and do a quick reminder. The chain rule is when you have a composite function. So I'm taking the derivative of f of g of x. I have a function within a function, these composite functions. This is equal to f prime of g of x times g prime of x. So it's the derivative of the outside times the derivative of the inside. So the chain rule really undoes that. So we are looking for an integrand that contains some function g of x and its derivative g prime x. So that's what we're looking for when we're trying to see if u-substitution will work. Let's go ahead and jump in, because sometimes example problems are the easiest way to start learning these problems or these sets. So let's begin with the following example. Let's say I have the integral of 2x e to the x squared plus 1 dx. So I'm looking at this function and I see something. First of all, I have a composite function, right? So e to the x squared plus 1 is a composite function. The outside function is e to the, just call it u, something. The inside component is the x squared plus 1. So that exponential, that e function is the outside and the x squared plus 1 is the inside. Then if I look at this and I say, okay, x squared plus 1, if I call that the inside of my composite function, which is happening up here in my definition, then is the derivative present? So the derivative of x squared is 2x. And if I look back into my original integrand here, I have a 2x inside there. So that's a clue that this is going to be a very good candidate for u-substitution. I have a 6-step process that I use to take the antiderivative or the indefinite integral when using u-substitution. So the first thing I do is choose u. So for this should be, in this instance, it will be the inside function. So when you have a composite function, it's the inside function that becomes u. So u is going to be that x squared plus 1. The second thing I do is take the derivative of u and solve for dx. So here I'm going to do du dx is equal to 2x. And then there is some kind of fuzzy math that happens here, but basically we treat du and dx as variables. and we kind of multiply them around to get dx isolated. So I would multiply dx over to the right-hand side. So I'd have du equals 2x dx. And then in order to isolate dx, I need to move the 2x over. And I divide. So I have du over 2x equals dx. So that is my second step. The third step is going to be to substitute, that's why this is called u-substitution, substitute u and dx back into the original function, or the original integrand. So I have, what I started with was the integral of 2x e to the x squared plus 1 dx. That's what I began with. I have now assigned u to be x squared plus 1, so that's where this will be. It will be replaced with u. And I have assigned dx to be du over 2x. So I will rewrite this as the integral of 2x e to the u times du over 2x. Now I'm very happy because the whole point of u-substitution is to eliminate every single x in your integral and replace it with u's, and then somehow get an easier function to integrate. So if I'm looking here, my fourth step is going to be to cancel all x's. So I will look here to my results, and I have a 2x in my function in my integrand here at the left hand of my integrand, and then I have a 2x in the denominator. So those two things actually cancel, and I end up with the integral of e to the u du. The next thing is to integrate with u as the variable. So I should note in this step, if the x's don't all cancel, there's a problem somewhere. So you can check your choice of u, check your math, or try a different method. Because it's possible that u-substitution is not the method of integration that you need. Here I have managed to cancel all my x's, so I am taking the antiderivative of e to the u du, and that ends up just being itself, e to the u plus c. I'm almost done with my problem. I was given a function that depends on x's, and I would like an answer that depends on x's. So the sixth step is to replace u with its value from part 1, from step 1. So in this problem here, I can scroll up. U was equal to x squared plus 1. So I will go ahead and replace my answer here. I will replace u with x squared plus 1. And I get the answer is e to the x squared plus 1 plus c. So that is kind of the most basic form of u-substitution. I do want to talk a little bit about this problem because we happened to be in a situation where the derivative of u, which was 2x, I had it over here, wrote it over here, it's in various locations. The derivative was actually exactly present in the original integrand. So that 2x appeared and canceled that all out. That's wonderful, but it doesn't always work out that way. In particular, the coefficients, the number in front of the x, they can be very flexible. When I take the derivative, I need to have the same number of x's. So here I have 1x, and then I had 1x in my integrand. They need to be the same number of x's so that they will cancel, because our goal is to cancel all the x's. However, the 2 there, or whatever the coefficient happens to be, that can be something a little bit different. So let me go ahead and just start an example of this so that we can see what happens when we have kind of that flexibility with the coefficients. So this is almost exactly the same problem. I will have the integral of 2x, and instead of e to the x squared, I'm going to have e to the 2x squared plus 1. So it's almost exactly the same problem. I still have a composite component, so I'm going to go ahead and choose that as my u. So u is going to be this composite piece, which is 2x squared plus 1, and then du dx is going to be 4x. Let's go ahead and solve out the problem. So I've already completed my first step here, which was to choose u. The second step is to solve for dx. So I'm going to have du over 4x equals dx. The third step was to substitute back into my original integrand. So I have my u that's going to get substituted in, and I have my dx, which will be substituted in. Oh, I only have half of my thing up here. Sorry. It will be substituted in up here for my dx. So once I do those two substitutions, I end up with 2x e to the u times du over 4x. And this is what I was saying, that you have to have the same number of x's. When I get to the fourth step and I cancel my x's, I end up with, I have 2x e to the u times du over 4x. My 2 and my 4 don't totally cancel, but the x's do cancel. And then I end up with 2 over 4 e to the u, which will be 1/2 e to the u. So just being aware that those coefficients are flexible. The important thing is that when I take the derivative, I end up with the same number of x's that are present elsewhere in the problem. And that did happen for me. I had here, let's see if I have another color. I have here, my derivative has 1x and my integrand has this 1x, and then those will cancel. So that's really what we're looking for. Just to complete this problem for completeness sake, the next thing we do is integrate. So I am taking the integral of 1/2 e to the u du, which will just be 1/2 e to the u plus c. And then the sixth step is to replace u. So I will end up with, I have 1/2 e to the u plus c becomes 1/2 e to the 2x squared plus 1 plus c. So just being aware that the problems, coefficients in particular, can be very flexible. Let's look at another example so we can get some practice with this process, and then we'll move into some more advanced type problems. So the next example I'd like to cover is the integral of sine of natural log x over x dx. Now, I often recommend to students that they separate quotients, they separate these divisions into multiple fractions because sometimes that really helps students to see what's happening. So if I pull this x out of the denominator, I can write it as 1 over x times the sine of the natural log of x. And one benefit of writing it this way is it shows students more clearly that they have first of all, we have a composite function. We have a natural log inside our sine function. So that's a function within a function. And if I take the derivative of natural log, I get 1 over x, which is present in my integrand. So those are kind of two clues that u-substitution is going to be a good fit. So I like to write it this way because it more clearly shows that. I'm going to go ahead and go through my process again. So I'm going to pick u, and I will have it always be, if you have a composite function, you should use that. So use the inside piece, inside component. So u will be natural log of x. The second thing we will do is take the derivative and solve for dx. So I have du dx equals 1 over x. I'll multiply my dx over to the right-hand side and then multiply my x over to the left-hand side, and end up with x du equals dx. The third thing I will do is substitute into my original integral. So the integral, and let me just go ahead and clearly explain where all my pieces are going. So we have the natural log of x is going to go in for u. I've already circled that one. And then the derivative, the dx here is going to be replaced with x du. So when I rewrite that, I'll get the integral of 1 over x sine of u times x du. The fourth step, actually, let's go ahead and write that on the next line here. So the fourth step is going to be to cancel or simplify my x's. So I end up with the integral of 1 over x sine of u times x du. I have an x in the numerator as well as the denominator, and this will end up being the integral of sine of u du. I now have a simpler integrand that does not contain any x's, and I can easily integrate because it's one of my basic integrals that I know the answer to. So the antiderivative of sine of u du is negative cosine of u plus c. And then my sixth step is to replace u with its value from step 1, which happens to be natural log x here. So this will be negative cosine of u plus c becomes negative cosine of the natural log of x plus c. Now let's look at some more advanced type of problems. Let's consider the following example. I have the integral of sine of x times cosine of x dx. There is no composite function. And that is one of the big clues that we've been using as to when we're using u-substitution. We're looking for a function within a function. However, I do have a function multiplied by its own derivative. So I choose that first function, whatever the thing is. So I have sine of x and the derivative of sine is cosine. So I will choose u to be sine of x. And then I will proceed with my steps and it's all going to work out beautifully. So the second step is going to be to solve for dx. So first I take the derivative. Du dx equals cosine x. And then I multiply the dx over to the right-hand side, and I divide by the cosine x to the left-hand side. So we had du over cosine x equals dx. The third step will be to replace, I should use the word substitute because it is called the substitution. So substitute into the integral. So I have sine of x equals u, and I have dx equals du over cosine. So I end up with the integral of u. The cosine x is not being replaced, but the dx is going to be replaced with du over cosine x. And now here I have a cosine divided by a cosine. So when I get to my fourth step, I cancel or eliminate all my x's. My cosines cancel, and I end up with the integral of u du. What could be simpler in terms of integrating a function? That is a very simple function. So then I integrate the antiderivative of u du. I use the inverse power rule. So I raise the exponent by 1, so you get u to this u squared, and then I divide by that, and then plus c. You could also write this as 1/2 u squared plus c. I don't think that it matters one way or another. Sometimes I like to bring them out as coefficients because it makes it a little bit cleaner to write, but that's fine. Either way is fine, I should say. And then the last step is to replace u from step 1. So this would be 1/2 u squared plus c becomes 1/2 sine of x squared plus c. Note that there is a shorthand for when you square trig functions, and it looks like this. So you bring that power kind of in, and it's sine squared x plus c. They mean the same thing mathematically, but this is the shorthand that you will see in textbooks kind of all over. This is a very standard format to put it, but they do mean the same thing. So let's do another kind of more complex example. I have 2 more that I'd like to cover before the end of the video here. I just want to be clear. What made this example complex was the fact that there was no composite function. So that's the first case that made this complex. And in this instance, we chose u to be the thing, kind of the the parent function. So I have something times its own derivative. We'll pick that first thing. So that way when you take the derivative, it will all cancel. So then the next scenario that can make these complex is if you have multiple composite functions. So let me go ahead and write this example up. I have 3e to the x times cosine of e to the x times the square root of sine of e to the x dx. So there are multiple composite functions. And what I mean by composite is those functions within a function. So here, my first composite function is this cosine e to the x. So I have that e function within my cosine. My second composite function is the square root of sine of e to the x. So this one is actually a 3-in-1 because I have first layer is the square root, then I have a sine, and then I have an e. So when you have multiple composite functions, choose u to be the inside of the function with the most layers. So this in the green, the cosine has 2 layers, right? One function within, so e within cosine. And this next one has 3 layers. It has e inside sine inside the square root. So I'm going to choose the entirety of my, when I'm looking at this 3-layer one, I'm going to choose sine of e to the x. So for u, I will have that entire thing inside the square root. So the only part that's getting left out is the outermost layer, is that square root. And then everything else is going to be my, that u value. Then I'm going to proceed and I'm going to start taking my derivative. So du dx is going to be equal to, this is a chain rule, so I have the derivative of the outside. The derivative of sine is cosine, so I have cosine e to the x times the derivative of the inside. The derivative of e to the x is just itself. This is very, very, very comforting for me. Cosine e to the x times e to the x. That is present in my integrand. So I know that I'm on the right track. In the second step of u-substitution, you should know if it's going to work. And the way you know is that all of the x's that are present inside my integrand are accounted for. I've assigned u to be the sine e to the x, and then my derivative is cosine e to the x times e to the x. So I have all my components. You don't have to do any more work if you get to the I mean, you do have to solve the problem. I shouldn't say you don't do any more work. You know if it's going to work by the second step. And then if it's not going to work, you can adjust course at that juncture. So here I'm going to solve for dx. So du is going to be divided by this whole thing. I'm going to go ahead and bring the e to the front just to make it a little more clear what's happening. So I have e to the x cosine x, and that's all equal to dx there. The third thing I do is to substitute. So I have, again, sine e to the x is my u. And then I'm going to replace, let's choose a different color, d of x, or dx, is going to be replaced with this whole big expression, the du over e to the x cosine e to the x. So when I substitute, I end up with 3e to the x cosine e to the x. That first part of my integrand didn't get any substitution. Times the square root of u times dx, which is also du over e to the x cosine e to the x. Now, when I go to my fourth step, which is to cancel my x's, I have my e to the x in the original function here, and then also in the denominator. So those cancels. I have my cosine e to the x, and then I also have it into the denominator, so those cancel. So I end up with the square root of 3 square root, or sorry, not square root, the integral of 3 square root of u du. I'm going to rewrite this as the integral of 3u to the 1/2 du, because this will make it easier for me to do step 5, which is to integrate. I will apply the inverse power rule to this 1/2, and I'll get 3 times u to the 3/2 over 3/2 plus c. I'm going to clean this up a little bit by doing copy dot flip with my fraction in my denominator. This is called multiplied by the reciprocal as well. So I end up with 3 times 2/3 times u to the 3/2 plus c, and those 3's turn into 1 when they multiply and divide. I cancel them. So I end up with 2u to the 3/2 plus c. And then my 6th step is to replace u from step 1. So here I have 2 times u, which is sine of e to the x, raised to the 3/2 power plus c. So this is the second advanced type of problem. The first was we didn't have a composite function. The second was we have multiple composite functions, and we have to address how to pick our u. The third type of advanced problem is that we run into a problem in step 4, so let's go ahead and look at that. So we have, for example, the antiderivative of x times the square root of x minus 4 dx. So we do have a composite function. So the square root of x minus 4 is a composite function. I do have an internal and external kind of thing. So the inside is x minus 4. The problem is that the derivative of x minus 4 is just 1. And I run into an issue because it's not going to cancel my x's. So let's go ahead and look. The first step is to pick u. So u is x minus 4. The second is going to be to solve for dx. So I'm going to have du dx equals 1. And then when I multiply my dx over, I just get du equals dx. Here's the issue. I have a 1, but I am at some point going to need to cancel this x that was out in the front of my integrand. So when you have something that's fairly straightforward as your component that you need to cancel, and I guess what I mean by that is when I get du just equal to dx, so this is simple, and this is simple. I can represent u, sorry, I shouldn't say it that way. I can represent x in terms of u. So when you have this, we are going to have to do extra work in step 4. Let me show you. So the third thing is always to substitute. So I have again, let me just be clear about what I'm substituting. I have u being x minus 4, and I have dx is just equal to du. So that's what's going to be substituted. So the integral of x times the square root of u times du. The fourth step is going to be to cancel the x's. I don't have anything present that can cancel. However, we can represent x in terms of u. Going back to my original selection for u equals x minus 4. Solving for x, I would add 4 to both sides, and I would get u plus 4 equals x. This is perfectly valid, and it has the internal consistency of my problem. So I assigned u, it is set in stone for this problem, but I am going to be internally consistent. So I can take this u plus 4 and I can plug it in for my x value. So I'm going to do that. I have x square root of u du. I can represent that as u plus 4 times the square root of u du. Now I have a function that depends only on u's, and I should be able to integrate and solve. In order to integrate this, I need to do a little bit of algebra. So I'm going to write this as the square root of u as u to the 1/2, and then I'm going to distribute it into my expression here. So u to the first power, so u times u to the 1/2, I add the powers, so I get 1 plus 1/2, so I get u to the 3/2, and then the 4 just becomes the coefficient, u to the 1/2. I want to be very clear. If we go back to the original problem, I am not allowed to distribute an x into a square root. That is not permitted. But I am allowed to distribute this square root into this other fraction. It matters what is underneath the square root. Is it a simple thing, just u, or is it a more complex expression? So I have achieved a simpler integrand, even though they look very similar, because I can do algebraic manipulation on this step 5 that I was not allowed to do on the very first step. So I want to be clear about what we've actually achieved in this problem. I will use the inverse power rule to take these antiderivatives. So 3/2 plus 1 is going to be 5/2. So I have u to the 5/2 divided by 5/2 plus 4 times u to the 3/2 divided by 3/2 plus c. We'll clean that up with those coefficients a little bit by doing multiply by reciprocal, copy dot flip, however you choose to remember this, to get those fractions out of the denominator. So I have 2/5 u to the 5/2 plus 2/3 times 4 times u to the 3/2 plus c. I'm almost done. My last step is to replace u from step 1. So I end up with 2/5 x minus 4 to the 5/2 plus, this 2/3, I can simplify that additionally, right? I can do it as 8/3, 2/3 times 4. And then I have my x minus 4 to the 3/2 plus c. So I'm able to solve this problem. And the key, I think what's going to happen? So you'll know that you need to do this extra work in step 4 when step 2 gets you, dx equals some constant times du. And then in step 3, you don't get all of your x's to cancel. So this is generally when you're going to have to do this extra work in step 4. So those are the 3 advanced type problems we covered today. So we did the basic type problems, which are pretty straightforward, and they involve composite functions. The next types were, the first advanced type was when we have no composite, but we do have a function times its own derivative. The next one was when we have multiple composite functions and we have to choose which of them to use, which of them to select for a u. And then the very last type was we have a composite function, but it doesn't work out to cancel all the x's. So can we represent whatever's kind of left over, this kind of leftovers? Can we represent that in terms of u? And if we can, then we substitute that in and proceed with our solving. So that is really kind of the gamut of the types of problems you're going to see in u-substitution. If it doesn't fit into one of these 3 categories and you run into a roadblock, then likely what is happening is that u-substitution is not an appropriate technique for the integral that you're working on. I'll do some more videos about how to do definite integrals with u-substitution, as well as additional integration techniques that you can try if u-sub is not appropriate.